In this video we're going to look at a couple of simplifications to the Euler-Lagrange equation. Now this is Euler-Lagrange equation written here. We also seen that whenever we derived the equation for a hanging rope, it gives us this functional form here, 1 plus y derived squared to the power of half times y. Now we mentioned whenever we did that this here has not got any explicit dependence on x, meaning there's no function of x within this. But it is explicitly dependent on y and y derivative. So if there's no explicit dependence on x, then we can rewrite the Euler-Lagrange equation in this simpler form, and this is called the Beltrami identity. And you can see it's simpler because the Euler-Lagrange takes 1, 2, 3 differentiations, and this only takes 1, so it keeps the maths a lot simpler. So let's go ahead and we'll show a proof of that. So first of all, what we'll do is our functional here is a function of x, y and y derivative, and the y is a function of x and the y derivative is also a function of x. So whenever we differentiate this functional with respect to x, we've got to use a chain rule. So we'll have partial f by partial x times dx by dx plus partial f by partial y times dy by dx plus partial f by partial y derivative times y derivative by dx. Now the first term here, the partial f by partial x is 0 because we've just said that there's no functional dependence of the function on x, so that's just 0. In this case here we've got a y derivative for this term and we've got y double derivative, so that whole thing can be written in this form here. Now we can rewrite the Euler-Lagrange equation. We can take this over to the other side and it just gives us Euler-Lagrange equation written in this form here. And then what we can do is the partial f by partial y, which is this term here, it can replace the partial f by partial y up here. So that's what I've done here. We're left with the df by dx equals the y derivative times the d by dx partial f by partial y derivative plus partial f by partial y derivative times y double derivative. So let's continue with this on the next page. So we've just rewritten that last line here. Now a thing to note, nice little trick, is that using the product rule in effect in reverse, the product rule for differentiation tells us that if you've got two functions that are multiplied, so say du times v, then that's going to be equal to u dv plus v du. So this is just the product rule for differentiation. So if we let the value u equal y derivative and the value equal v equal partial f by partial y derivative, then we've got this here term below, because you can see here on the left hand side we have the d is the d by dx and the u is the y derivative and the v is the partial f by partial y derivative. So that there is just this term here. But if you look at above here, if we look at u dv, well, u is just the y derivative, which is this term here, and the dv is just this differentiated with respect to x, it's d by dx partial f by partial y derivative, and also the v du is going to equal, well, the v is going to be the partial f by partial y derivative, and the du is a y derivative differentiated again, which gives us a y double derivative. So that means that this whole thing here is just equal to this here. Now what we can do is we can take this whole thing across to the other side, so you'd have the partial, you'd have the df by dx minus d by dx y derivative partial f by partial y derivative, but the df by dx is just the d by dx and you can put the f inside the brackets, so we're just left with this term here. But this whole thing is equal to 0, so whenever you differentiate whatever's inside this brackets, you get a value of 0. So the only thing that you can differentiate that gives a value of 0 is a constant. So this whole thing that's inside the bracket here must equal a constant. So therefore we can say that this value f minus y derivative partial f by partial y derivative equals a constant, and this is the proof of the Beltrami identity. So now we have our second simplification. If we had a function here which had no explicit dependence on x and there's no explicit dependence on y, so the only explicit dependence is on y derivative here, and that's an example of it here, then we can say then that we can rewrite the Euler-Lagrange equation is simply partial f by partial y derivative equals a constant. So we'll go and have a little show the proof of that. So if we were to write the Euler-Lagrange equation down, which is rewritten here, now we know that there's no dependence of f on y, so there's no explicit dependence on that, so we can just get rid of this first term here, so we'll simply be left with this term here. But we know that whenever we differentiate what's inside this bracket here, we get a value of 0. Now the only way we can get a value of 0 is if this, what's inside the bracket here, is actually equal to a constant, because when you differentiate a constant you get 0. You differentiate 5, you get 0. So that means that whatever's in this bracket must equal a constant. So we can simply say partial f by partial y derivative equals a constant. So that's our second little simplification. So let's go ahead in the next slide and we'll look at a summary of what we've learned. So in summary, if we have an explicit dependence on x, y and y derivative, then we use the Euler-Lagrange equation. If we have an explicit dependence on y and y derivative only, then we can use the Beltrami identity. If we have an explicit dependence on y derivative only, then we can use this simplification, partial f by partial y derivative equals a constant. So these will be very, very handy, or you've already seen from the examples that you've worked through that these simplifications are very, very handy and they simplify things a great deal. So thank you for listening. I'll get you on the next video. Goodbye.